Hi everyone. In this video I will be talking about descriptive discriminant analysis using SPSS. In this presentation I will cover reasons why discriminant analysis may be used, procedures for carrying out descriptive discriminant analysis using SPSS, and interpretation of results from a descriptive discriminant analysis. A copy of the data used for this presentation and this PowerPoint, which is going to contain more information than I cover in the video, will be made available to you as links underneath the video description, so be sure to download them to follow along. If you find the information I provide useful, please consider liking the video and sharing it with others. So what is discriminant analysis and why is it used? Discriminant analysis is aimed at identifying characteristics that discriminate among different groups. In particular, a central focus is on determining what predictors or combinations of predictors create maximum separation among groups. Discriminant analysis can be used for one of two purposes. Predictive discriminant analysis, or PDA, is used to create and test a rule designed to predict group membership based on a set of predictor variables. Descriptive discriminant analysis, or DDA, is used for descriptive or explanatory purposes, whereby the analyst seeks to describe group differences on a set of response variables. Now, discriminant analysis may be used as a standalone procedure for description or prediction, or it may be used as a follow-up to a MANOVA. And in the context of MANOVA, an analyst often chooses to follow up a significant test result by seeking to identify those variables upon which groups differ. And a conventional, albeit dubious, approach that is taken is to perform multiple one-way ANOVAs to compare groups on each dependent variable. This approach generally ignores one of the main reasons for performing the MANOVA in the first place, and that is to account for the intercorrelations among the dependent variables when making group comparisons. Moreover, this approach is potentially problematic as MANOVA and ANOVA were developed to address different types of research questions. So when the analyst chooses to use descriptive discriminant analysis as a follow-up procedure to MANOVA, the aim is on describing or naming the dimensions on which the set of dependent variables differed. Notably, things can become more complex with DDA as the dependent variables may combine in multiple ways to create differences along multiple dimensions, some or all of which may need to be described. Now, in the context of discriminant analysis, when you have only two groups, there's only one linear combination of predictor variables that can produce separation between them. However, in those cases where you have more than two groups, the maximum number of linear combinations that can produce separation is either A, the number of predictors, or B, the number of groups minus one, whichever happens to be the least. Also, in the context of discriminant analysis, a linear combination of predictors is referred to as a discriminant function, and group means for the discriminant functions are referred to as centroids. So what kinds of questions do you ask when performing descriptive discriminant analysis? First, is there evidence of mean differences among groups on the composite variables or discriminating functions? And if so, how many dimensions account for any observed separation among groups on the predictors? Second, if there are differences on any of the dimensions, what is the relative ordering of the contributions of the measured variables to the discriminating functions? Moreover, what do these discriminating functions represent or mean? And can we name them or provide a coherent description of those functions? Third, how do we describe how groups differ in terms of those functions? And what do higher versus lower group means on the functions actually represent? So now let's transition and go into a couple of examples using SPSS where we fundamentally are addressing those questions. So for example 1, we're going to have students' performance goals, achievement, and mastery goals serving as predictors of their gender identification, which is a binary variable which is dummy-coded 0 for identified male and 1 for identified female. The second example, we're going to have students' performance goals, interest, achievement, and anxiety serving as predictors of mastery goals, where mastery goals has basically been trichotomized from the continuous mastery variable. So the variable is actually mastery LMH, and it's an ordered categorical variable coded 1 for low, 2 for medium, and 3 for high. Now, before we get started on this, let me just note that this is generally a bad idea in terms of converting continuous measures into categorical ones in this fashion. You end up losing a lot of information when you do this, but this is just to provide a demonstration of the procedure. Also, let me note that none of the proposed relationships that I'm testing were derived from any substantive theorizing. So again, the model specifications are made solely to demonstrate the procedure. So we'll start with example 1. Again, we're going to be predicting students' gender identification from performance goals, achievement, and mastery goals. So let's open up SPSS and specify our model. So here we have our data set, and we're going to be using performance goals, achievement, and the mastery goal variable here as predictors of gender identification. Again, 0 is reflecting persons identified as male, 1 for identified as female. So to run our analysis, we're going to go to Analyze, go down to Classify, and then go down to Discriminant. We'll move our dependent variable gender ID to the grouping variables box, and where it says Define Range, we're going to click on this box, and the minimum and maximum values are 0 and 1, since there's only 2 groups in this data set. So we'll click on Continue now, and so you can see it highlights up here 0 and 1. And we're going to move our predictor variables over. So we'll move performance goals, achievement, and mastery over to the independence box. We'll click on Statistics, and we'll ask for means, univariate ANOVAs, and then boxes M. And boxes M is used to test the assumption of homogeneity of population covariance matrices between the groups. So in other words, the assumption is that the variances and covariances of our predictor variables are equal across the 2 groups. Under matrices, we can obviously ask for various matrices. I'll just go ahead and click on within groups correlation, within groups covariance if you want to study those. Click on Continue. Under Classify, we'll click on Summary Table down here, and so this can be useful for basically evaluating the model in terms of how well our proposed model leads to correct prediction of group membership when it comes to our dependent variable. So next we'll click on Continue, and then we'll click on OK and look at our output. So scrolling down, you can see under Group Statistics, we have gender ID 0 and 1 reflecting persons identified as male and female respectively. So you've got the means and standard deviations for each of our variables. When we scroll a little bit further, we have tests of equality of group means, and these are one-way ANOVAs, basically comparing group differences for each of our predictor variables. When we scroll down a little bit further, you can see we have boxes tests, so within this table right here. And basically, again, it's testing the null hypothesis of equal population covariance matrices. So essentially, if this is indicating statistical significance, then we would have evidence that we have a violation of the assumption of equality of population covariance matrices. If it's non-significant, as we have right here, then we would infer that the assumption is met. So in this case, it would appear that our assumption is met. So we'll scroll down a little bit further and look at the summary of canonical discriminant functions. And as I noted earlier, the number of discriminant functions will equal the number of predictors or the number of groups minus 1, whichever is least. So we had 2 groups, so we're only going to have a single discriminant function. So you can see right here the canonical correlation reflects the relationship between our discriminant function and the grouping variable. Down here, we have a test of the functions. And so with only a single discriminant function right here, this is fundamentally a test of a significance test associated with the canonical correlation. Now note too that the canonical correlation is going to range anywhere from 0 to 1, and you can see right here that our canonical correlation is pretty low. In terms of its significance, you can see right here that the p-value is greater than our conventional 0.05 level. So it looks like that the discriminant function doesn't do a very good job in terms of accounting for differences between groups. Now, ordinarily, if we would say that our discriminant function is contributing to between group variation with respect to our predictors, then what we would do is we would go down to these next tables, the standardized canonical discriminant function coefficients and structure matrix, in order to either name the discriminant function or to basically kind of assign a relative ordering when it comes to predictors in terms of their relative contributions to the discriminant function. So we're not really going to name our discriminant function. Again, we have non-significance right here, so there's not really a whole lot of point in going any further. But just in the interest of kind of further describing what these coefficients are, we'll just go ahead and look at, first off, the standardized canonical discriminant function coefficients. These are analogous to beta coefficients in the context of multiple regression. And so essentially we can take the absolute value of these associated with each of the predictors and then assign a rank ordering of the predictors in terms of their contributions to the discriminant function. And Pittock and Stevens actually suggest a threshold of 0.30, or a loading criteria of 0.30 in absolute value as indicating that we have a predictor that's contributing substantially to the discriminant function. So you can see right here that basically performance goals and mastery goals, both of these coefficients exceed 0.30, and you can see with mastery goals it is less than 0.30. Moreover, you can see that performance goals would be contributing to group separation more than the achievement variable. But again, there's not really a whole lot of point in talking about this because, as I said before, our discriminant function was not significant. With respect to the structure matrix, these are basically correlations between each of our measured variables and the discriminant function. And so if we wanted to name the discriminant function, if it had been significant, that might be something that we want to do, in which case we could basically utilize a loading criteria of 0.30. I think Petthauser uses that criteria in his book. I think Tabachnik and Fedel use a loading criteria of 0.33. So basically all of our predictors, you can see right here, are loading really above both of those potential thresholds. But again, we're not going to name the function because there's not really a whole lot of point in doing so at this time. We'll scroll down. You can see that we have functions at group centroids. So these are basically the means of the discriminant functions for each of our two groups. So this is for persons identified male, that's the mean for the discriminant function. For those identified as female, that would be the mean as well. So you can see that males would be scoring higher on the discriminant function than females. And so if we had named the function and given it some kind of meaning, then that would be, we would basically be saying that males were scoring higher than females with respect to whatever that meaning happened to be. Scrolling down a little bit further, you can see that we have our classification table. And essentially you can see that in each row, we have the number of individuals who were actually identified as male is 32, and 108 individuals were actually identified as female. Then you can see the columns are reflecting the predicted group memberships. And so essentially you can see that we had 18 individuals who were actually identified as male were correctly predicted by the model to be identified as male. And we had 64 individuals that were actually female that were correctly predicted by the model to be identified as female. So if we want to talk about the percentage in terms of the accuracy rate, you can see that we have 56.3% accuracy when it comes to predicting individuals identified as male, and we have 59.3% accuracy when it comes to predicting identification as female based on our model. So now let's move on to example 2, where we are testing a model where we have several variables, that is performance goals, achievement, interest, and anxiety, that are being considered as predictors of whether a person falls at low, medium, or high levels of mastery goals. And again, we're going to be using the mastery LMH variable. So in this case, we have essentially 3 groups on our dependent variable, and we have 4 predictors. So the maximum number of discriminant functions will be 2. So now let's go back to our data set and run the analysis. So here we are back at our data set. Our dependent variable is going to be this one right here, and our predictors will include performance goals. Then we have achievement, followed by interest and anxiety. So let's run our analysis by going to Analyze, go to Classify, and then go down to Discriminant here. I'm going to click on Reset, and I'm going to move my Mastery LMH variable over to the Grouping Variable box. And the values on this variable range from 1 to 3. So we're going to click on Define Range, and we'll type in 1 for the minimum and 3 for the maximum. We'll click on Continue. We'll move our predictors over to the Independent box, our Independence box. And then we'll click on Statistics. We can ask for the same things that we had asked for before. We'll click on Continue here. Then under Classify, we'll go ahead and click on our summary table. And then now that we have more than a single discriminant function that's going to be produced, we can also plot out the discriminant functions by clicking on Plots Combined Groups right here. We'll click on Continue and then on OK. So now when we scroll down, first off, let's just take a quick look at Box's test. You can see that the p-value that's given is 0.161, which is greater than the conventional 0.05 level. So we would infer that the population covariance matrices are equal across our 3 groups. Next, we'll scroll down to the summary of canonical discriminant functions. And so now you'll notice that we have function 1 and function 2. And basically what happens when we have more than a single discriminant function, each function that is extracted will account for successively less amounts of variation between the groups. So the first function, you can see that it accounts for 94.4% of the total between group association between the predictors and the outcome. And the next function accounts for an additional 5.6%. So the total variance between group variation accounted for is 100%. So the first canonical correlation is 0.632, and then the next one is 0.196. So you can see that the first function would have the largest canonical correlation, the second one would have the next largest, and obviously if we had more discriminant functions, they would continue to decrease. Now, so you can see that basically the first function has a pretty substantial relationship with our grouping variable. Now, if we want to test our functions for significance, we do that by going down to this table again. We'll slam the table right here. And you can see that we have functions 1 through 2 and then 2. And what this is reflecting is a peel-off procedure for testing the discriminant functions. So the first test, this first chi-square test, is a test of the combined effects of functions 1 through 2. So the Wilks lambda value that you see right here is actually also the same Wilks lambda that you will find in the MANOVA table if you were comparing the groups on our variables. And so you can see that this test is statistically significant. So at a minimum, we can say that at least one discriminant function would be producing separation between the groups. Then you can see that we peel off that first discriminant function that accounts for most of the between association, and then we have a test of just the second function. So here you can see that that test of that function is not statistically significant. So what that's going to tell us then is that essentially the first discriminant function is significant, whereas the second one is not significant. So when it comes to interpreting the discriminant functions, then we only really want to interpret the first discriminant function and not the second one, because the first one is doing most of the work when it comes to separating the groups with respect to our predictors. So scrolling down, we have our standardized canonical discriminant function coefficients in our structure matrix yet again. But in this case right here, we don't really want to bother ourselves with trying to interpret function 2 because that's not really contributing to the discrimination between the groups. So adopting a loading criteria of 0.30 with respect to the standardized canonical discriminant function coefficients in structure matrix, we can see that basically achievement and interest is substantially loaded onto the first function, really in both matrices right here. So there it is again in the structure matrix. Using the standardized canonical discriminant function coefficients, we can see that achievement is contributing most substantially to that function, followed by our interest variable. With respect to the structure matrix, we can also again see that we have, in this case, achievement followed by interest in terms of their relative contributions. We do see anxiety kicking in with a slight negative association with that function, and it would meet the loading criteria using Petthauser's criteria. But again, you can see that the lion's share of the work with respect to defining the discriminant function is accounted for by achievement and interest. So we might name that first discriminant function something like academic investment. Now, if we scroll down, you can see that we have our functions at group centroids. So this is function 1, and again, the centroids are reflecting the means for our discriminant functions. So these are the means for our 3 groups for our mastery variable. That's low, medium, and high mastery. And then there's function 2 right there with low, medium, and high mastery as well. And there's not really going to be, you can see that there's not a whole lot of separation in the means of the discriminant functions on that second dimension, whereas you can see a much more substantial differences among those means on the first function. We can also visualize this by scrolling down, and you can see the discriminant function. So you can see that we have essentially function 1, which is reflected on the horizontal axis, and then function 2 reflected on the vertical axis. And so you can see a substantial spread among our 3 groups with respect to the centroids on that first function, whereas there's very minimal spread when it comes to the second function. So if we kind of scroll back up and look at our functions at group centroids, you can basically see that, remember, if we name that function, function 1, academic investment, then what that would be telling us is that essentially students that were in the low mastery goals group were lowest when it comes to the academic investment, whereas those students that are that are highest in mastery goals would have the highest levels of academic investment. Then obviously the academic investment for the middle group is falling in between those 2 other groups. Finally, scrolling down to the classification results, you can see that we have 81.3% of those individuals that were that fell in the low mastery goals group were correctly predicted to fall into that group by the model. You can see that 35.6% of those individuals falling in the medium level of mastery goals were correctly predicted by the model. And then we had 74.3% of those individuals falling into the high group were correctly predicted to do so based on the model. So the overall classification accuracy, or the hit rate, is 55.4%. But you can see that where our hit rate is really suffering is due to problems with predicting membership in the middle mastery goal group. Okay, so that's going to cover everything that I wanted to talk about in this particular video. Again, there's more information that's available in the PowerPoint, so I do encourage you to download it. I also include a number of references as well. So again, if you liked the video and you found it useful, please like it and also share it with others. Thanks for watching.